I'd like to take you on a brief tour of a working drilling rig, just in case some of you don't get the opportunity to visit a working drill site when the drilling operation is going on. Let's take a look at this simple animation which will describe the main mechanical functions of the drilling rig. First of all, we're going to need a drill floor. And the drill floor will be suspended well above the ground, leaving room for important equipment beneath the drill floor. To get access to that, we'll need some steps up and a cabin of some sort to contain all the controls for the drilling rig. Sometimes that cabin is referred to as the doghouse, and that's where the driller will stand and do his work. And then we have above the drill floor, we have the main drilling derrick. This is a very tall mechanical structure designed to accommodate up to 90 feet of drill pipe, which will be screwed together, typically in 30-foot sections, and then used to drill the well. Inside the drilling derrick, we'll have two vertical rails attached to the framework. These vertical parallel rails are used to provide stability for the top drive, and the top drive is a large, powerful engine which provides the torque to turn the drill pipe while we're drilling. Next to the rig, there will be a supply of drill pipe and a long horizontal section known as the catwalk, where the drill pipe is rolled onto the catwalk, ready to be pushed or pulled up into the drilling derrick. In this case, a little mechanical arm is pushing the drill pipe up the ramp, ready to be pulled up into the main derrick and screwed to the next piece to continue the drilling operation. Beneath the drill floor, we'll have a blowout preventer. The two primary components of the blowout preventer that we would be interested in are the pipe rams, the lower one in blue, and the blind rams, the upper one in red. While we're drilling, the drilling fluid is pumped down the inside of the drill pipe. It escapes through nozzles at the drill bit at about 200 miles an hour, cleaning the hole and carrying the chippings up the outside of the drill pipe back to surface. If we were to take a kick in the well, and let's say gas came into the well bore, it would find its way up the annulus. As it's coming up the annulus, small bubbles of gas would be getting larger and larger, and so we can detect this by seeing that there's more fluid coming out of the well than we're pumping into it. If we see a kick like that developing, we can close these lower blue rams, the pipe rams. They're basically two rubber horseshoes designed to just close enough to choke off the annulus, but not tighter than that. So they're really closing around the drill string. If that fails to control the kick in the well, then the upper ones might be deployed. Now this is a real emergency situation because the upper ones, the blind rams, will actually shear the pipe in half, closing off the well completely, and then very often it's a case of drilling a relief well. Okay, so that's the blowout preventer. As far as we're concerned, though, the general day-to-day operation won't be using either the pipe rams or the blind rams, but we will be using the drawworks. Now, the drawworks is really just a big drum of cable which has a band brake shown in green, and that maintains a high level of friction on the drawworks. The cable coming off the drawworks drum goes right up to the top of the derrick. It has multiple wraps in a block and tackle arrangement attached to the top drive. And that allows us then to release the brake and gravity will take the equipment down the hole. However, that's also attached to a very large engine. and that engine can power the drawworks to pull the equipment out of the hole. We'll see how that functions in a moment. And then, of course, we've got the drill string. And the drill string will consist of a bottom hole assembly, which I've drawn here in yellow, and the drill pipe, which I've drawn in white. Now, if I release the brake and raise the brake here, gravity is going to make the equipment go down the hole. If I apply the brake, then everything stops. And the more I release the brake, the faster the top drive will descend. If I then engage the clutch from the main power engine to the drawworks, now when I release the brake, equipment is coming back up out of the hole. So in very simple terms, with the brake released, the top drive is free to move. With the brake engaged, the top drive is no longer free to move. If the engine clutch is disengaged, then all the drill string will descend down the well when we release the brake. If the clutch is engaged, we're picking up the drill string. Then we're also turning the drill string, and now we're turning and ready to go down on bottom and make hole. So here are some of the main components then on the real rig. There's our steps going up to the doghouse cabin. Here's the drilling derrick here. You can just see the top drive there with the cables above it, the ramp, the drill floor, and so on. Let's take a look at another one. Here's a rig where everything can be delivered to the site with just a few truckloads. And here's our catwalk here. The drill floor here. There's the top drive, cables above that. The doghouse is quite small in this case and set at drill floor level, with some of the rest of the controls down in this cabin here at ground level. In here we've got the mud pumps, we've got the blowout preventer, hidden from view is the drawworks drum, and the steps going up to the drill floor and so on. Everything in one very compact unit. Here's the mechanical arm pushing the drill pipe up the ramp through what we call the V-door into the main rig. By the way, there's no such thing as a door in the V-door, so if you're sent for the keys for the V-door, just ignore the request. Here's the steps going up to the drill floor, and we'll now go and take a look on site.
Welcome to the rig site. Let's just go up to the drill floor and we'll see what's going on.
Now here's a view of the instrumentation inside the doghouse, and all the information that the driller needs for his job is made available to him on various digital screens. There's an important one for us, that's the weight on bit indicator, and also had in there the mud pump pressures and so on as well. That's a joystick for controlling the top drive position. And then we've got pressures, weight on bit, rate of penetration, and so on, all being logged in real time as we drill. Here's a view then upwards from the drill floor to the top drive above us. There are the steel rails that keep the top drive steady against the derrick. This is sometimes referred to as the monkey board, and on this rig we can stack quite a large amount of pipe in these brackets up here, and the top drive picks them up from this level and then continues the drilling operation. Here's the drill floor itself, and here are the slips that are used to grip the drill pipe and hold it in place while we screw the next section in. We'll see those in operation very shortly. Here's the drawworks, and there's the big drum of cable, and you can just see on the right hand side here, there's the cable going all the way up to the drilling derrick, top of the drilling derrick. In this section here is the band brake that applies the friction to the drawworks, and then behind here is the big engine that will apply power should we engage the clutch. Here's a weight on bit indicator. This is really just a weighing machine. It's measuring the load hanging on the hook at top drive level, and when weight comes off the hook, we assume that that is going onto the bit. So it's really just showing us the difference between the off bottom weight and the on bottom weight when the bit is in contact with the bottom of the well. I'm now going to show you a short clip of the process of making a connection on one of the rigs that I've visited recently. You can skip this if you're used to watching this operation. It's not the most exciting thing you've ever watched on a video, but if you haven't seen it before, it's quite an interesting process. You can see here the top drive is just about to reach the drill floor, and when it does, they'll come back up off bottom. There they are, just coming back up, maybe just 2 or 3 feet, and the roughnecks will then move in and place the slips in to hold the pipe in place while they unscrew that section of drill pipe. So here are the slips moving in, and the slips will grip the drill pipe just with the force of the weight of the drill pipe pulling it down, and the teeth on the slips will cause it to grip and hold it in place. Then the driller will turn the pumps off. You can see the hoses relaxing there, and obviously with the hoses full of drilling fluid, if you didn't turn the pumps off, you could have 1000 psi trying to escape from the drill pipe when we disconnect from the top drive. So the pumps go off, and then the top drive goes into reverse, and the drill pipe is then disconnected. Some drilling fluid will escape, but the guys are ready for that, and they'll clean that up, and they'll always make sure that none of the drilling fluid escapes from the drill floor and blows out onto the surrounding countryside. There's the top drive turning in reverse and unscrewing that section of drill pipe. Now as it lifts off, there's some fluid escaping there, but now the section of drill pipe that's sitting in the slips is gripped by the slips with the whole weight of the drill string beneath that. They're just cleaning that up, and that'll be a mud filter. Yes, there's a mud filter coming out from that section, and they'll pop it into the next section that's going to be lifted in place. Now on this rig, they'll always have the next section ready in a separate mouse hole just to the right of the main well, and they'll bring in the elevators, just a set of clamps really, to lift that up. They have to release the slips from the mouse hole. Now this happens every now and again, that the slips don't separate, but we have a very sophisticated scientific method of releasing that, usually involving a 16-pound sledgehammer. So that's it released now, or is it? No, not quite. Yes, now it is. And they'll lift that out and pull the slips out, and now the next section of drill pipe, which has been stacked there in the mouse hole, is ready to be pulled up the derrick and screwed on to the previous section of drill pipe. You just saw the joint there at the end of the first 30-foot section, and the top drive is going all the way back to the top of the derrick, ready to start drilling the next 90 feet. Yeah, just making sure that that drilling fluid doesn't blow all over the place. It's quite a windy day. So then the roughnecks will line up the threads and then bring in a tool called the iron roughneck, which grips the bottom piece of pipe and turns the top piece of pipe to exactly the right amount of torque to ensure that it's structurally sound and also completely watertight and able to withstand the pressures of the drilling fluid inside the pipe. That's quite a quick process, so they'll release that. And we're now ready to carry on drilling, and up at the top drive connecting again. Here are the mud tanks, and here is the mud engineer. Now, of all the people working on the drill site, the mud engineer is the one deserving of the greatest sympathy. Their job is a thankless task, only paid attention to when things go wrong, and we blame most things on the drill site on either the mud engineer or the geologist. But the drilling fluid that we use, which is a mixture of clays and chemicals and either oil or water, it's such a complicated process, and it's carrying out so many different tasks. It's not just our carriage medium for carrying the chippings up the outside and cleaning the hole. It's also our pressure balancing system, and we have to choose the weights of the mud very carefully to make sure that we're balancing the pressures in any of the formations that we're likely to encounter as we go down the wellbore. Similarly, the fluid has to be the right consistency, because the viscosity of that fluid is going to make a big difference to the pressure profile as we go down the hole. That's what this little cone is used for here. By pouring the fluid into the cone and measuring how long it takes to escape from the bottom, that's a good measure of the viscosity. And if it starts to get too dry, then the mud engineer will add water. In this case, this is water-based mud on this rig. He'll add water to reduce that viscosity. He's also making sure that the temperature of the fluid doesn't get too high. Clearly, it's going down into a warm well. It will come out of the well warmer, and then we're circulating it down again. So in this particular rig, there's an open grid river of drilling fluid, which is letting steam escape out to the atmosphere. But the mud's tasks don't just end there. We're also using the mud as our communications medium. So when we're measuring with MWD, a valve downhole is opening and closing, creating a pressure pulse to give our survey information a binary code that we can detect at surface. And so the mud pulse telemetry requires that we have the right sort of consistency of mud for us to be able to send that to surface without too much attenuation. Similarly, the mud is also used as our power source. If we're using turbines or mud motors, then it's actually the mud pumps themselves that are providing the power by pumping the fluid down the well to actually drive the drill bit. So with all these different tasks, and there are several more, carrying lost circulation material down and so on, the mud engineer has a difficult balancing act to carry out when he's designing the mud for the system. Here's a water-based mud, and there's the open grid, where if you could see this in animated, you would see the fluid flowing through here and the steam coming off through this grid out to surface, cooling it down. Here's the test cone for oil-based mud on this particular rig, and if we look down into the tanks there, you can see the oil-based mud circulating through the system. And here are a few experts on the rig. Here are the shale shakers, and their task is to clean up the drilling fluid, and so it's really just a set of vibrating sieves that clean out the chippings, and the drilling fluid then passes through the sieves and is recirculated back down the hole. Two operating in parallel. It's quite interesting to see the volume of chips coming through. That's quite a high penetration rate. When the chippings are cleaned up and ready for disposal, they really should have very little oil left on them, and you can see in this short clip just how clean we can make them if we put the effort in.
That is amazing. You gotta do it again.
Well, I mentioned that the drilling fluid is also our communications medium, and this is a typical screen that we might see at surface from the MudPulse telemetry system. At the moment, this directional driller is sliding the drilling assembly down hole with the tool face, that's the angle from the high side of the hole of the bend in the assembly. He's pointing that to the low side right on a tool face of 136 degrees right. You'll all be experts in tool face after a presentation on understanding tool face later in the program.
This rig is a land rig based in West Texas, and right now we're drilling the lateral section of an 18,000 foot measured depth well at 9,000 feet of TVD into a fairly thin zone. So we need a good rig with a good crew and good tools, and most importantly we need good quality surveys to be able to land that well properly and stay in the reservoir while we're drilling.
Now here's a couple of good examples of a good crew. On the left, Mr. Ted Cottrell, one of the legends of the industry, and on the right, Anne Fitzgerald, a young drilling engineer, and it's just great to see experience being passed on from one generation to the next. Here's the blowout preventer underneath a rig up in Arkansas. And here are the pipe rams on the lower end, and then above that the blind rams. Hopefully you never have to press the red button to close the blind rams, but the pipe rams, if there's a gas kick in the well, then the gas will accumulate down here if we close the rams, and then we can open up this valve to called the choke valve to a flare and allow that gas to bleed off. Now, in a short course like this, we're not going to make you experts in bit selection, but there are generally two main types of bit that we'll use downhole, and this would be a hard rock bit. It's a tri-cone or roller cone bit, and each of these teeth here are made from tungsten carbide. They're very hard indeed, and so the whole weight of the drilling assembly is resting on very, very small areas, creating a very high stress in the rock, and it fractures the rock rather than scraping it. It fractures the rock into small chippings, and then the drilling fluid is escaping through these nozzles. These are just plastic covers to protect the nozzles while it's out in the open air, but the mud is normally jetting through here and cleaning the hole, carrying the chippings up to the surface. This would be a softer rock bit called a PDC bit. PDC means polycrystalline diamond compound. And the polycrystalline diamond compound is actually this material here in little coins, if you like, on the end of these teeth. And as the drill bit turns, clockwise. Drill bit's always turned clockwise. This is scraping the surface of the rock. You can sometimes tell when you're looking at the shale shakers whether or not it's a PDC bit or a tricone bit that's down there by the shape of the chippings that are coming up to the surface. Here are the nozzles in this case, and again the drilling fluid jetting out about 200 miles an hour will help to keep the hole clean. Now, it is possible to drill hard rock with a soft rock bit, but it's not possible to drill soft rock with a hard rock bit. What tends to happen, that might sound counterintuitive, but if you use a hard rock bit in soft rock, it creates so much in the way of chippings that you can basically cement the hole in. It cuts through it like butter. And so we have to choose the right drill bit for the job to make sure that the penetration rate is optimized. Here's a drill bit after it's been downhole and it's pretty worn out. You can see here it's old and battered and has no teeth left. I suddenly feel a sense of empathy with this drill bit. Here are some drill collars. These are the components that actually provide the weight on the bit. When we are drilling, normally the majority of our drill string will actually be in tension, and it's the weight of these big heavy collars resting on the bit that produce the weight on the bit. Here are some of the other components that we need in the bottom hole assembly. This is an interesting section. This is a mud motor in here, and then you can perhaps see there's a slight bend in this part of the assembly. And the mud motor is it's like an Archimedes screw. It's a twisted stainless steel rotor, and the drilling fluid passing through here creates a torque in that motor that turns the drill bit. And through this bend, there's a flexible steel rod or maybe a universal joint chain, but some method of transferring that rotary motion to the drill bit, which is attached to this bearing at the other end. This is an MWD unit. There are some non-magnetic collars in there as well to make sure that the MWD is separated from the steel in the drill string. There's a better view of the bent housing at the end of the mud motor section, and you can see it's quite a small bend, but in practice this assembly suitably stabilized will give us build rates of up to 9 or 10 degrees per 100 for every 100 feet that we drill down the well. This is an interesting tool, and this is one of the reasons I was visiting this rig. This is a new rotary steerable system, and everything up here is turning, but this sleeve here is a non-rotating part that makes contact with the hole wall. And these pistons that you see here create a side force. Now, there's actually 3 of these, or maybe 4 on this one. I think it's 3. 3 sets of pistons, and they'll create a differential force at a given tool face. And so the non-rotating part is in contact with the hole wall, and everything else is rotating through it. So it creates a side force on the bit, which is attached down at the lower end here, and that side force creates the curvature. This is a very clever design, and rotary steerable systems have been around for about 20 years now, but they've improved in technology dramatically. Here's the directional driller sitting in his cabin, and he has screens which act as repeaters for everything that's happening up on the drill floor. And so his job is to keep an eye on the weight on the bit, keep an eye on the tool face, collect the surveys, and make decisions about whether or not he's going to change the tool face or rotate or steer the next section. So his is a very important job, and all of you are going to get the chance to use a directional drilling simulator on this course so that you too can have a little bit of the experience that the directional driller has in steering the well towards its target. I'd like to squeeze in an interview with Ted Cotterill. You'll like Ted. He's got loads of experience, and I'm going to ask him about that new rotary steerable system.
Hi Ted, we've just come in off the drill floor from the rig here in West Texas, and I just wondered if you could tell me, first of all, what it is that you're doing here on the rig. What's your particular responsibility?
Angus, I'm out here to oversee the running of an experimental rotary steerable tool.
Now that's pretty exciting. Is this one of the first wells that this tool has been used on?
No, it's not. This will be the 8th well for Pioneer, and every time we run it, our performance level exceeds the prior run.
Excellent. And what's the arrangement of the tool? Is the tool being run on its own, or is it being run with a motor behind the tool to give you more flexibility on the rotary?
Yes, we run a motor behind the tool that turns out about 90 RPM, and then we add 70 from surface. So we turn the rotary steerable tool, or the bit is turning around 160, and sometimes we run it up to 200, but that's about its limit.
I'm interested to know then, on the BHA that you're running, you'll then have behind that rotary steerable and behind the motor, you're going to have the MWD. So how far back is it from the bit face to where the MWD sensors are actually measuring the inclination and azimuth?
Well, that's been something that we struggled with in the prior 7 runs, where the MWD was the third component in the drilling, the bottom assembly, and the survey sensor set 75 foot behind the bit. So on the prior 7 runs, we've run the MWD tool on top of the motor, which is on top of the rotary steerable tool. The surveying sensor is 75 foot back from the bit, and that's been somewhat problematic, being so far back and being able to steer the tool. So in this 8th run, we run the MWD tool between the rotary steerable tool and the motor. And in this position, the survey point is 29 foot back from the bit.
29.
29. Now the rotary steerable tool is all non-magnetic, so there's no interference on the bottom side.
Yes.
Above the survey point in the MWD, we have about 60-some feet of Mon-El for isolation from our motor.
Okay, right. With the original runs, when the sensor was so far back, what sort of build rate were you using to get up in the curve with the tool? Or are you only using the tool in the lateral?
We're only using the tool in the lateral.
Okay,
but sometimes we will hit a 4-degree per 100 push, and you can go a long ways, 4 or 5 degrees.
Yes.
In a short period of time. And when you don't find out about that till 75 foot to 100 foot later,
yes,
we have to work hard to get back in line with the planned azimuth direction of the well.
Okay. Well, thank you very much, Ted. It's been really nice chatting to you, and thanks for inviting me down to the rig here.
Well, enjoy the U.S., especially Texas.
Thank you.
So there we have it. There are the main components that you need to be aware of. We'll do a separate presentation to take you through the controls of the simulator, but now you'll have an idea of what's actually happening on the drill floor as we simulate these different activities.